Okay, so today we are continuing our discussion about non-parametric tests. In particular, we're going to talk more about Wilcoxon tests. So, last class we said that there are alternatives to the t-tests, right? We have 3 different types of t-tests. We have our one-sample t-test, our independent t-test, and our paired t-test. And these t-tests depend on the assumption that the population from which they're being sampled is normally distributed, or that our sample size is large enough so that the law of large numbers will kick in and we'll have something that is basically normally distributed anyway, something that we would expect to be normally distributed. But that's not always the case. Also, with our t-tests, typically we are working with interval or ratio scale data. Not necessarily ordinal data. Sometimes you only have the ordinal data available. So if you have the ordinal data available, you're not really justified in doing a t-test. But you could do something that uses ranks, something that uses orders. So the Wilcoxon family of tests are going to be our alternatives to the t-test. So we have a one-sample Wilcoxon signed rank test. We have a Wilcoxon ranked sum test, which is equivalent to the Mann-Whitney U. The Mann-Whitney U and the calculation, there's some slight differences, but the answers that you will get with both of these will give you the same thing. Will give you the same answer, same p-value. Okay, finally for our paired t-test, we have a Wilcoxon matched pairs signed rank test. If you see in some article or something, and it just says Wilcoxon signed rank test, they are probably talking about this one as opposed to the one sample version. So if you don't see one sample or matched pairs or dependent or something to clue you off which one it is, it's probably going to be this one that people are talking about. Okay, these are all based on ranks. All based on ordinal scale data. Now let's jump in and do some analysis. So let's do our one sample Wilcoxon signed ranks test. This is the same thing that we did last class. We did this example last class. I'm going through it again to make sure you guys understand this in relationship to the other. So we had our data. So there's our data. The mean on the homework that I gave you was like the median equals 10. Last class I talked about the mean equaling something as opposed to the median. A little bit later we'll see why some sources will say you're testing a hypothesis against the mean and others say you're testing a hypothesis against the median. Anyway, for now that's really unimportant. So we have our data, we have our null hypothesis, and we can use Wilcox.test to test our hypothesis. And we don't have to give Wilcox test the ranks. We don't have to compute the ranks. We don't have to find the differences between our data and the hypothesized mean or median. So that's nice. We can just work with the raw data. Okay, so we give Wilcox test our data. We tell it what the median is. We tell it that we want exact to be true. This actually isn't such a big deal unless you're going over a sample size of 50. But it's a safe practice. Okay, so we did this last class. I think we used a different hypothesized mu. But here it is with the hypothesized mu of 6. So here are the results. So what should we do?
Reject.
We should reject the null. If we're using the traditional alpha level, which is 0.05, 0.009 is less than 0.005. So we should reject the null. Sweet. Okay. So let's do, now instead of doing our one sample t-test alternative, let's do our independent t-test alternative. We're going to use the same data that we did before. But imagine that that same data set came from 2 different samples. S1 and S2, right? So we have 2 different samples. This is from sample 1, sample 2, sample 3, I'm sorry. Sample 1, 1, 1, 1, 1, sample 2, 2, 2, 2, 2. So the first 5 observations came from sample 1, the second 5 came from sample. Okay, would, at least the standard law would be that the median of the groups are equal. Right? Just like with the independent t-test, the null hypothesis was that the mean of the two groups were equal. And we could restate this as a difference. Right? We could say there's a difference between group medians that equals 0. Right? No difference. Just like with the independent t-test, we could specify other differences if we had some reason to believe that there should be a particular difference. So we could do that by specifying the mu here as well. So in order to do this, there are a couple different ways. So I'll show you one that is similar to the format that you guys used for ANOVA. So we have Wilcox test, DAT. So DAT, that was this. DAT is what? DAT is a function of sample. So we're saying DAT is broken down up into these samples. So we're going to look at the DAT for S1 and the DAT for S2. So DAT is a function of sample, exact equals true. If our null hypothesis is that the difference is going to be 0, we don't need to specify mu. So we're good to go. And here are the results. What should we do?
What is the
We'll talk about W in a minute. We should fail to reject. Why?
Because it's
P-value is greater than 0.05. It's 0.22, right? So we should fail to reject. We'll come back to what W is in just a minute.
Can I ask you?
Yes?
If we have median is different than 0, where will we put it and in which sign? I mean, will we multiply or we will just...
If you wanted, like, if you thought that the difference between the group medians was like 10, then you would put mu equals 10.
And come.
Come on? Okay. Or this is sort of the way that you guys are more used to seeing things, right? We had separate samples. So here we have sample 1, S1 is DAT. So that big long data thing that we had before. DAT, where the sample equals sample 1. So that goes through all of the data and only takes out the pieces of data that are associated with sample equaling S1. And then we do the same thing for S2. Right? So now instead of just saying, okay, we're going to analyze DAT as a function of sample, we can say something like this, that is much more similar to what you guys have seen previously, right? So T.test, sample 1, sample 2, boom. So we got the same thing here. Wilcox test, sample 1, sample 2. So you can do it either way. If you have a data frame and you have a factor that indicates what sample things are from, it can be easier to do it like this. But if you aren't comfortable doing like that, you can do it the way that you're most comfortable with. So you can pull out the pieces of the information from the first sample and pull out the pieces of information for the second sample and specify them specifically in Wilcox test. Okay, so if we do this, let's see what we had before. So we had W equals 6 and a p-value of 0.222, so we should get the same thing if you can do it either way. So W equals 6, p-value equals 0.222. Notice here, data, it says S1 and S2, right? We have our sample 1 and our sample 2. Earlier we had something a little bit different. Data was our data organized or grouped by sample. Okay? All right, so again, we should fail to reject. We have the same values there, so that's pretty sweet. Okay, let's move on to our alternative to the dependent t-test.
Okay.
Our paired t-test, right? So the samples. With the paired t-tests, we had our samples set up in such a way so that the first observation in the first sample was paired with the first observation in the second sample, right?
Yeah.
Yeah, okay. So we're going to want to have our data set up in the same way. So if we're setting up a sample 1 and sample 2, make sure that you have the pairs in the same order so it knows which ones should be paired together. Just like the previous null hypothesis, we can again say that the median of the groups are equal, or rephrase this as a difference between medians. The difference between the groups' medians is 0. Or we can also say that the median difference between groups is 0. So to run this in the new way, we'd say Wilcox.test data as a function or as grouped by sample, that equals true, paired equals true. Just like when we were doing a paired t-test, we said t-test, whatever we were testing, paired equals true. We're doing the same thing here to tell R that these are matched pairs. Okay? Okay, so we do that, and here are our data. Fail to reject. Yes?
We didn't indicate, but in independent test, we were saying that var equals variance are equals to. But here we didn't do var.
We didn't say that var is equal. So, can you hold off on this question for a little bit? I'm going to talk about the assumptions in just a couple slides about the Wilcoxon test. So when I talk about symmetric distributions, ask me about the variance, okay? All right. So, she's exactly right. Previously, we'd say things like var equals true, right? If we were assuming that var equals true, and that was for the independent test. Okay, but we didn't do that for the Wilcox test alternative, and we'll see why in just a minute. Okay, so we should again fail to reject because the p-value is greater than the traditional alpha. If we were using some different alpha, if we were using an alpha of 0.7, we would reject the null, although that would really be crazy. Anyway, so here we have done all 3 different types of Wilcoxon tests. And just like we were able to do the independent t-test alternative, that is the Wilcoxon rank sum test with the 2 different formulations, we can do the same thing with our Wilcoxon sign rank test. So here we have it. Data is organized by sample, data by sample. We can also do it as Wilcox test S1, S2, exact equals true, paired equals true, and we'll get the same answer that we did before. D equals 5, P is 0.65, 5.65, same thing. All right, failed to reject. Cool. So the paired t-test was equivalent to doing a 1 sample t-test on the differences. Do you guys remember that? When we were dealing with the t-tests, we said that the paired thing was special because we could subtract one thing from the other. And this allowed us to decrease the variance, right, in the differences. If they weren't dependent on one another, you would actually increase the variance by subtracting them. But since they are dependent on one another, we were able to pull out, throw away part of the variance that was related to differences between subjects. And we said that if we ran an independent t-test, we could run a 1 sample t-test on the differences and find exactly the same answer. So let's see if this works here too. Because if this is really sort of an alternative to the paired t-test, then maybe we should expect to find something similar. So let's see. Will it work? So here's what we did last, right? Wilcox.test for sample 1, sample 2, it's paired. And now what we're doing is we are doing a Wilcox test for the difference between sample 1 and sample 2. And we're just getting differences here. So this is just a bunch of differences. We're doing a 1 sample Wilcoxon signed ranks test on the differences. Boom. Notice here the data are S1 minus S2, not S1 and S2. But look, v equals 5, p-value, exactly the same thing. It works. So let's talk about the details. How we get the things that we're getting. How we're getting the p-values. How we're getting the v's and the w's and what those things are. So last class we talked a bit about the details for the one sample test, right? We said that v is equal to the sum of the ranks for the scores that were greater than our hypothesized mean or median. Right? And we said that we are going to rank the scores by their absolute deviations from the hypothesized medians. Let's go over this one more time. So we have the raw data, right? These are the raw data that we're working with. So this would be DAT. If you type out DAT in R, you can see these values. Now our hypothesized median was what? It was 6, right? So which of these scores are less than 6? Only 4.5, which I have highlighted nicely for you, right? So we start with the raw data. Then what we need to do is we can sort it now, or we can sort it later. I think I'm going to sort it later today. I think what I did today, I took the deviations. Deviations, what are the deviations?
We will each scores subtract from cycles.
So for each score, we're going to subtract the hypothesized mean or median. So minus 6, that should equal 1.1.
Minus 1.5.
1.5. And so on and so forth, right? So there we go, 1.1. Negative 1.5. Sweet. And we have the rest. Okay. So now I sorted things. You could have sorted things earlier if you wanted to. It doesn't matter if you sort before you find the deviations or after you find the deviations. Whatever. Okay, so I didn't just sort the deviations, I sorted the absolute deviations, right? So if you were going to sort here, you would need to sort things again based on the absolute deviations because we want the ranks of the absolute deviations, right? So you can sort earlier or later, but you need to make sure that your final sorting is based on the order of the absolute deviations. Okay, so what should go first?
1.1.
1.1?
No, we have 0.2.
0.2. Is anything smaller than 0.2? No. So 0.2 should go first. 1.1. 1.5. And then the rest of it. Right? Notice we have the absolute value of the deviation here as opposed to the sign deviation. Okay, now what? This is the easy part. Rank them. Okay, what's the rank for 0.2? 1. How about 2? And so on. Chocolate. What's the final step? We need to sum the ranks that are associated with the scores that were greater than 6. So I color-coded, right? All the black ones were greater than 6. So all we need to do is just sum up the black ranks, right? So if we do that, 1 plus 2 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10, that will give us 52. 52. Let's see what we had before. 52. V was 52. So V really is the sum of the ranks for the scores that are greater than the hypothesized mean or median. All right. Okay, so we found 52 before and we found 52 now. So we know how to find V if we had to do it by ourselves. Cool. So the intuition behind this, like, what is intuition? Is that what your question was? What is intuition? Can anyone define it? Yeah, I'm struggling with the same thing. You want to try? So intuition, someone please Google this while I'm trying to explain it. So basically intuition is like a way to understand something. Like the understanding sort of...
It's like pre-feeling?
It doesn't necessarily have to be a pre-feeling. Like you can talk about some type of like preliminary intuition, like you have a feeling something will happen in the future. But you don't have to have intuition just about that. Like math, like 2 plus 2. You have an intuition that like 2 things plus 2 things should be 4 things, right? It's intuitive. Yeah. So did anyone find a Google definition?
Yeah.
What is it? Oh, sezgi.
You got it.
Alright, so what does that mean in Turkish? Define it for me.
Pre-feeling.
Pre-feeling. You use Google Define, because pre-feeling I think is a bit...
No, I just made up like feeling and says we use it for pre-feeling. That you feel that it happens.
You will have it. Will happen.
I'm able to understand or know something without needing to think about it or using to discover it.
Maybe I should change this. So if you didn't hear it, you said a way to understand something without having to think about it?
Yeah.
Well, the intuition. There is little, so let's reason about it and think about it instead. Okay. Okay, so last class I said the mean. Then if you notice on the homework it said the median. If you watch the video, I also put a note up that said the median. And in this class I come in and I say the median or the mean. Think about what a median is. What is the mean? Yes? It is the value that is in the middle of everything else in what sense? Is it the balance point?
It's not, it's balance point was the mean.
The balance point was the mean. The median was the point where if you ordered all of the scores, right? Put all of the scores in order. The one that's in the middle, that's the median. Where if there are 2 that's in the middle, it's the mean of those 2, right?
But the median of the ranks is the same as the mean for the balance point. Because you have ranks, you have the order of them, then you find the median for those, it's the same as the balance point.
Is that right? You have things in order. Let's take a really simple example. So you have 2 ranks, 1 and 2. What's the mean of 1 and 2? 1.5. What's the median? 1.5. Well, let's say you have 1, 2, 3. What's the mean? 2. What's the median? 2. I haven't thought about it that way, but yeah. Do you have another question? Okay. So, if the hypothesized median is the true median, half of those deviations that we calculated should be above it, and half of them should be below it, right? So, okay, this is the symmetric thing, and this is the part that I told you to ask about the variance. So let me read this first, and then we'll talk about variance. If the distribution is symmetric around the median, this doesn't mean that it's normally distributed. If it is just ranks by themselves, if it is just ordinal rank data, it will be a uniform distribution, where each value has the same probability of occurrence, right? But symmetric around the mean or the median, right? So if we have a distribution that is symmetric around the median, the mean will equal the median. So you are justified in hypothesizing about the mean or the median. Does that make sense? So we have some distribution. Here's the median. And the the distribution is uniformly distributed around, I'm sorry, not uniformly, symmetrically distributed around this median. So it could go like this, it could go like that, it could be normal, it could be anything else, but it's symmetrically distributed around the median. If that's the case, then the mean and the median will be the same thing.
Yeah.
Okay? So this is why, when I was taught about the Wilcoxon, I was taught about in terms of the means. And then a lot of the sources I was looking at kept referring to medians. I'm like, oh right, because the median, half should be above and half should be below. But then it turns out with this extra assumption that the distribution is symmetric, then you have something, you have the mean equaling the median, and you also have the variances being equal, because the variances for a set of ranks, if you have the same number of ranks, you're going to have the same variance. Okay, so if the distribution is symmetric around the median, then on average, the sums of the positive and the negative ranks should be equal to one another. Right? Half of them are going to be positive, half of them are going to be negative, but we don't just care about negative and positive, we want the absolute deviations, right? But if it's distributed symmetrically, you're just as likely to get a large negative one as a large positive one, or a small negative one as a small positive one, right? So you should, if the median really is the true median, the hypothesized one is true, then what you should find is that the sums of the positive and negative ranks should be equal. So it should be basically half of the sum of all of the ranks. If you summed up all of the ranks and divided by 2, right, you should get, on average, the sums of the positive and the negative ranks. So what we are doing when we are calculating V is we get the sums of one of those. Now, just like degrees of freedom, if we know one set of ranks, we will know the other set of ranks. If we know what one sum of the ranks is, we will know what the other sum of the ranks is, because we know how many data we have in total. We can calculate the total sum of the ranks, right? So values of V that are much greater or lower than this will lead us to reject a two-tailed null hypothesis. If we had a directional hypothesis, we would only reject if it is extreme in the right direction. Right? Okay, so the test assumes symmetry around the median. If it's symmetric, the median will be the mean. We already said this. Okay, so let's move on. Oh, right, so if this turns out not to be true, there are other tests that you can do. All right, so we just talked about, I guess not the intuition, but the reasoning sort of behind what we're doing with our one sample Wilcoxon. What other Wilcoxons should be similar to that? The two sample? Should the two sample be similar to that? With the t-test, we had similar logic for 2 of our tests.
Independent.
We said one test was basically just a different test. One test was the same as the other. But we the one sample and the pair. So if we understand what's going on for this, we should hopefully have an idea about what's going on for the paired version as well. Okay, let's talk about the independent, when we have independent samples. So this was our test that we did. Wilcox test, S1, S2. We didn't say paired equals true, right? Not saying paired equals true, it's going to perform the independent version of the Wilcoxon test. Okay, so we have W equals 6. And she asked, what is W?
The sum of the two V's.
The sum of the two V's. So sum of the positive and sum of the negative?
I mean, you have like the mean of 2V from 2 samples. So,
The V that we had before, this isn't a mean. It's a sum.
It's the sum of the values that are greater than the mean.
Right.
Okay, so we have a v of the first sample
Uh-huh.
and the v of the second sample. We just have to find the mean for those two, or just have to find it by the same way we found the sample 2 and sample 1 mean with the independent test, t-test.
It's a bit different from that. This one is sort of odd. I think this is a little less intuitive than the previous one. But it's fairly easy. When you see us do the demonstration, you'll see exactly what we're doing and how you do it. Anyway, what we're going to do for each rank we have in sample 1. So we're going to rank our samples again. We're going to take each rank in sample 1 and then count how many of the sample 2 ranks are smaller. And W is going to be the sum of all of those individual counts. Scores, the ranking of these is very intuitive. It's just rank them from lowest to highest. So let's take a look at this in just a minute and find out the rankings. So imagine we have our raw data. I said that the first 5 were S1, the second 5 were S2, right? So we have our raw data. We can sort the data. Which one should go first? So 4.5 is the smallest.
6.2.
6.2. And then we've got the rest of them, right? So we're just sorting them as you would anything. We're not subtracting anything from them. We're just sorting them as they are. Okay. All right, so we have them sorted. How do we rank them?
Where is the absolute difference?
With absolute differences or anything?
Okay, so just 1, 2, 3.
1, 2,
Yeah.
3. Yes, that's right. It's really easy. You just rank them as if they're all from one thing. Okay? Now we need to make some comparisons. So I said that for each rank in sample 1, we count how many of the sample 2 ranks are smaller. So for each rank in sample 1, here's a rank for sample 1. How many of the sample 2 ranks are smaller than this rank?
0.
None of them. That's the smallest rank, right? We're going to go and do that for each of the ranks for sample 1. So here are our sample 1 ranks. We have 1, 3, 4, 6, 7. Let's make sure this is right. 1, 3, 4, 6, 7. And we are going to compare each of these sample 1 ranks against each of the sample 2 ranks. So we have 2, 5, 8, 9, and 10. 2, 5, 8, 9, and 10. Okay? So let's find the number of sample 2 ranks that are smaller than each sample 1 rank. So you guys said that there's nothing smaller than that. So the number that we have is 0. How about the number of sample 2 ranks that are smaller than 3?
1.
2.
1.
1.
This one, but it's number 2.
That's right. 2 is smaller than 3. So that's 1. 1 rank is smaller. Is 5 smaller? No, we just have 1, which is from 2. Okay, so we have 1 rank that's smaller than 3. How about 4?
1.
Again, we have 1. 2 is smaller than 4. How about for 6? 2 is smaller than 6, and
5.
5 is smaller than 6. Are any of the others smaller? No. So how many ranks do we have that are smaller than 6? 2. How about 7? 2. And 5. 2. Right, so 2 and 5 are both smaller than 7. Now, so we have the number of ranks that are smaller than each of the sample 1 ranks. And now we just need to add them up. That's why I said W should be. W should be this. And before we had W was equal to, in my head, I'm getting old, I don't remember. 6, okay, so it was 6, so we should have 6. 0 plus 1, okay, it's 1 plus 1, it's 2 plus 2 is 4 plus 2, it's 6. It works. Woo! So that's what W is. Now for the non-intuition of what's going on here. What? Do I not have the... Weird. The intuition is missing. Good job saving it, William. All right, so what's the intuition then? What should happen if the two medians are the same and the distribution is uniform around the medians?
The sum should be equal
The sums should be equal?
around the.
But what are we summing? We're summing these comparisons, right? How many of these comparisons should be less?
5.
How many of the sample 2 ranks should be less than the sample 1 ranks? 0? Let's see if I can do an example. This is going to be difficult. Say we have 6, 5, 4, 3, 2, 1. So this, well, this is not exactly what I'm, let's see, that's equal to 10, and this is equal to 11, right? If we look at the comparisons, so this is basically, they're very close to being the same thing, right? If they're both coming from the same median, then what we should have is the sums. So you mentioned the sums earlier, right? The V's. The V's, the sums for the one sample should be basically equal to the sums for the other sample, if there really is no difference, right? So here we have, it's not exact. In my example, I believe I had it in something where we had it exactly adding up to one another. But let's take a look. So if we have 6, 3, 2, and we have 5, 4, 1, 5, 4, 1, 5, 4, 1. Notice we're making, here we have 9 comparisons that we're making, right? So, how many of them, if there really is no difference, on average should be less than the sum motives? 3 out of 9?
9.
9 out of 9. All of them should be less. Well, here we have a pretty equal balance. Let's see. How many are less than 6? 3. How many less than 3? How many are less than 2? That equals 5. Right? 5, which is pretty close to 4.5. Pretty close to half of those comparisons are less than the sample one, right? So for the example I had, I think I started with like 12. And you ended up getting exactly the same number of numbers, the same number that are less as are greater. So if they really are equal, you should have basically, on average, if they're truly equal, you should have the same sums, and you should have basically the same number of ranks that are smaller as are greater, right?
So we're comparing now 5, 12, 25. In this way.
9.
So here we have,
5.
let's see, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So we have 25 comparisons. If these things were really sort of balanced, we should have about 12.5. Let's do this quickly. I think we can do this. Right, I don't have, I was so caught in that, I don't want to use that again. Do you see it? Okay. So let's do this. So we have 10 ranks. So let's try to evenly distribute them. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. So we have 10, 7, 6, 3, 2, 9, 8, 5, 4, 1, 9, 8, 5, 4, 1, 9, 8, 5, 4, 1. And you guys are clever enough to fill that in. Okay, how many are less than 10?
5.
5. 5. 5. How many are less than 7? 3. 5 plus 3. 3. 1. And this is equal to, that's 13. Is that right? Yes, 13. Which is pretty dang close to 12.5.
So our intuition is that rank 2 should be an average all smaller than the highest in rank 1.
I'm sorry, could you say that again?
So we should, our intuition is that rank 2 values, rank 2 are an average, they are all smaller than the highest rank 1. Like in this sample, when you have 10, they are all lower than 10, and they...
So here, not all of them are lower than 10. About half of them are lower than 10. Right? I mean, if you had something really extreme, imagine that you had a situation where you didn't... have things equally distributed. Instead, you had something like this. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. What's your W?
25.
Your W would be 25, right? So as your W gets a lot bigger than I guess, half of the number of the comparisons that you're making, then this suggests that you are moving away from what you were expecting. Similarly, if you have the opposite, right, where you have 1, 2, 3, 4, 5, and these are 6, 7, 8, 9, 10, you're going to have 0, right? So as you move away in either direction, right, either direction, so you can do one-tailed hypotheses, okay? So does that make sense to sort of what we are doing? The farther away that we get from half the number of total comparisons that we have, the more atypical, the more extreme the sample is. Now we haven't gone into the sampling distributions of V or the sampling distributions of W. We could do that. We are not going to. We do not have enough time. But hopefully you guys sort of understand intuition. It's the same thing like a T. If the null hypothesis was true, you'd expect a T that's very close to 0, right? And the farther it got from 0, the more extreme that was. The smaller the p-value. Here, you're not looking for a difference from 0, you're looking for a difference from basically half the number of the comparisons that you're making. Did I say something wrong? All right, so our dependent sample details. First, we take the differences between sample 1 and sample 2 scores. And then V is the sum of the ranks for the differences that are greater than 0. Just like the one sample version. Unless we want to specify some particular difference. If we want to specify a particular difference between the mean or the means, then we can change mu appropriately. But the idea here is basically exactly the same, except you are not looking at the scores themselves, you are looking at the differences between the scores. Yes?
What are we comparing V to?
So V here again is going to be the sum of the positive scores. Just like the sum for without the mu specified. This is for a null hypothesis that there is no difference, right? So there's no difference. So if we take a difference and that difference is negative, then we're going to rank the absolute differences, but we're going to remember which of those differences come from a positive difference and which of those come from a negative difference, right? And then we will sum up the ranks that correspond to the positive differences. Just like in the one sample version, we summed up the ranks of the ranks that were associated with the scores that were above the hypothesized mean and median. Yeah.
No, just when you said about the independent one, we have like, instead of t is equal to 0, it's not close to 0, it's close to half of those. It's not the t, it's not
Right.
close to 0, it's like it should be close to half of those, like 12.5 for example. Our value, our W.
Right.
We compare it to the half of the value that we have in the samples.
So in the samples, we had 10 values in the samples, right? But we were actually making 25 comparisons.
Yeah, okay, but 12.5 is the half, right?
Yeah, half of the comparisons that we were making. So we made 25 comparisons, half of that's
We're
12.5.
comparing W to half of those comparisons. We comparing W to
Yeah, we're comparing W to the half of those comparisons.
which is 12.5.
For that, for this example, yes.
Okay.
When you have 10 ranks, it will be 12.5.
What about V?
What about V? What are we comparing V against? So what are we comparing V against? So let's go back to the English. English. Sorry. If the distribution is symmetric around the median, then on average, the sums of the positive and negative ranks should be equal.
So we should have a
So, again, half of the sum is related to half, right? The sum of all the ranks. So, the sum of 1 to 10. Can someone do that for me? 1, 2, 3, 4, 5, 6, 7, 8. Oh, I'm so dumb. There's a rule for doing this. Okay, so 10, we have 20, 30, 40, 55. 55. So we have, right, 10, 9 plus 1 is another 10, 8 plus 2 is another 10, 7 plus 3 is another 10, 6 plus 4 is another 10, and then we have the 5 and 9. All right, so this is going to be, the 55 is going to be the total sum of all of the ranks, right? So if the ranks are evenly balanced out, then on average what we should find is that we, 55 divided by 2, so that's 27.5. So we are comparing V against
27.
half the sum of all of the ranks. That's it? Okay, sorry. I think I was making it more
No,
complicated.
because when you give the example of T, is we're comparing to 0. As close as it gets to 0, then we fail to reject.
Yeah, the reason I use V is not because we're using 0 here. We're using something else, but to demonstrate that we are using something. We're using what we are expecting. If the null hypothesis is true, what on average, what in the long run would we expect to occur? So based on this expectation, how far away something is sort of gives us an idea about how extreme it is. Now if we really want to understand how extreme the different V's and W's are, then we need to actually compute the sampling distributions of the V's and W's. Have fun. You can. I'm not going to for this class. In fact, I didn't even teach you how to actually calculate the normal distribution. I never told you the formula for that, or the formula for the t-distribution. We did some sampling to see that it looked like the function that R was telling us. never actually calculated it. Why? Because for some of these functions, you need to have an understanding of calculus, especially when you want to calculate cumulative probabilities. So, or probabilities that go from here to there or someplace else. You need calculus for that. But I'm not assuming that you guys know calculus. I've taken calculus, but I'm not an expert at it. So we let R do that heavy lifting for us. I'm happy with the understanding of the idea, the non-intuitive intuition. So that's basically it. So this dependent sample is basically the same thing as the one sample, except for looking at the differences between the pairs, as opposed to the raw data by themselves. All right, next class we will do 2 or maybe 3 more non-parametric tests, and then that's it. On Wednesday we will have a review. On Friday we will have an exam. Then we will have a break for a little while, and then you have an optional cumulative final, which most of you should probably take. All right, have a good weekend.